So it's now my great pleasure to formally introduce Dr. Ian Smith. So Dr. Smith is a highly experienced climate scientist and lecturer who spent many years working in CSIRO and the Bureau of Meteorology. He has published extensively in the scientific literature on climate variability, climate change, climate predictions, and long-term climate change projections. He now runs a small consultancy and he works part-time with the University of Southern Queensland's Centre for Applied Climate Sciences. Dr. Ian Smith, it is a pleasure to welcome you to the floor.
Thanks very much for that welcome, Anika, and welcome to our audience, Gigi and Kelly. Hopefully this is a useful talk for you both. So please, if there's anything you're not clear on, please use the chat function. And Anika, could you let me know if there are any questions come up during the talk? I'm
absolutely.
Happy to answer them as we go through.
We also have Nano here too.
Yeah.
So you've got three.
Three, okay. Who's the third person?
So we've got Nano Moody.
Okay, welcome to Nano as well. That's a very good, nice introduction. What I'll be doing is talking about past, present, and future climate, with a bit of an emphasis on Western New South Wales. And the region of Western New South Wales, as we've defined it, is indicated in the little graphic here, which identifies the area, including Broken Hill, Burke, Cobar, Wentworth as towns indicated. Don't worry about that slide. I'll come back to that later on. That's just to indicate the region that we're looking at. You know who I am, and this talk has been put together with the considerable assistance of colleagues Scott Power, Kate, Sharmila and Nina from UniSQ. The information I'm presenting might be familiar to you all because you've undoubtedly be aware of some of the things I'm talking about, in particular El Nino, La Nina events, the basics of climate change, and there's lots of information out there which you can access, plenty of publications and sites. But I've distilled down this talk into just under an hour, hopefully a little bit less, to give you my perspective on the major issues. And I think it's useful because following this presentation, there's the opportunity for you people and others in the region to participate in a discussion session dealing with impacts of climate change, whereas I'm just focusing mainly on the raw essentials of climate change, temperature and rainfall. I'll touch a little bit on impacts, but that's something that is for a later discussion. Here's the overview of the talk, and my task is to try and get it condensed down into 55 minutes, hopefully. Don't worry if I skim through it a little bit at the end. I'd rather leave a bit of time for you guys to ask questions about things I've touched on. So it's two parts to the talk: the past, and essentially the present and the future. And in talking about the past and the present, we're looking at climate variability, how has it changed, and what we think caused the changes. Yeah, this is an interesting slide because it's got maps of Australia corresponding to the years 1970 right through to 2021. And the colours on these maps indicate where rainfall for that particular year was either above average in the blues or below average in the red colourings. And you can see the highly variable nature of rainfall. There's never rarely an occasion where the whole continent is blue or red, or even white. There's always patches of above average and below average rainfall in any year. But I'd like you to look at a few years in particular. If you cast your eyes down to the bottom of the screen and to the far right corner, you'll see the year 2019. And that's an unusual year because most of the continent is covered in red, meaning below average rainfall. And in fact, averaged over the whole continent, that was the driest year on record, not just going back to 1970, but going well back to the early part of the 20th century. Not only was it the driest year on record, it was also the warmest year on record. So that indicates that we might be dealing with something related to climate change, because what scientists do when they see these maps is to try and tease out any patterns in the rainfall distributions. We're looking for signals and trends, and there's evidence of a trend in that possibly things might be getting drier, but they're definitely getting warmer, that's for sure. And we're looking for patterns of variability. And if you cast your eyes across to the left-hand side of the screen and look at the years 2010 and 2011, there were 2 years which were relatively wet over most of Australia. And the point here is that those 2 years corresponded to what we call La Nina events, and the year 2019 corresponded to an El Nino event, or a drought event, contrasting with La Ninas, which are wet events. And I imagine that once we put down, or the Bureau puts down the map for 2022, you will see a map with a lot more blue on it, particularly over the east and north of Australia. Now, I mentioned those years, and what I've shown you here on a timescale, I'm not sure if you can read the years on the bottom, but they go from 1970 right through to 2021. And what's shown on the bar charts here is Wilcannia annual rainfall. So it's the amount of rain collected at Wilcannia over the whole 12 months. And for each year, you can see variable. I'll just focus now on the interesting years, which I've highlighted in colour. All the bars are black except for the 2 red and the 2 blue bars. The 2 blue bars are the La Nina years, 2010 and 2011. The red bar on the right is 2019. That was the dry year for Australia as a whole. And the one further to the left is the 1982 El Nino event. So what this tells us is that typically the annual rainfall at Wilcannia is about 250 millimetres, say. And during La Nina years, it can be up to double that. And during El Nino years, it can be, as in 1982, almost half what you get normally. So we can see what appears to be a strong El Nino, La Nina effect on Wilcannia rainfall. And we know that there is, in fact, a strong effect over much of Western New South Wales. This phenomenon has a big impact on the rainfall there. So I've talked about El Nino and La Ninas. Again, you might already know all about this, but it doesn't hurt to reiterate that when I mention El Nino or La Nina, that's really referring to what's happening in the Pacific Oceans, in particular the sea surface temperatures. During El Ninos, there's a certain pattern of temperatures across the Pacific Ocean. And in La Nina events, there's an opposite pattern with consequent impacts on rainfall each side of the Pacific. But in addition to the sea surface temperatures, we also have oscillations or variations in the pressure patterns across the Pacific Ocean. And we measure these pressure patterns using the recorded barometer pressures at Darwin and Tahiti. And the variation in those pressure patterns are referred to as the Southern Oscillation. The variation in the Pacific temperatures are referred to as El Nino, La Nina events. But because it's a combined coupled event, all these things are tied up together, the whole phenomenon is referred to as El Nino. The El Nino Southern Oscillation events, where EN stands for the El Nino or the ocean component, SO, the Southern Oscillation, refers to the atmospheric component. And in detail, what happens is that if you look at what happens during these contrasting events, we can see in these two slides on the left, we've got what happens during a La Nina event. And during a La Nina event over our part of the world, the temperatures to the north of Australia, the sea surface temperatures there are warmer than normal. And they are, on the other side of the Pacific Ocean, they're cooler than normal. And because they're warmer than normal over this part of Australia, that contributes to more convection and more rainfall over this part of the world. And as a consequence, we have an increased chance of above average rainfall over Australia. And in association with those sea surface temperatures, there are changes in the winds along the equator and changes in in the pressure patterns. In La Nina, we have Southern Oscillation Index is positive, and vice versa for El Nino. And the El Nino situation is on the right, and you can see here it's a contrast. There are cooler than normal temperatures to the north of Australia. That tends to suppress the convection that takes place over this part of the world and reduce the amount of humidity and the amount of moisture available for rainfall over Australia. And we tend to get below average rainfall and often severe droughts. Then you cross over to the other side of the Pacific, and of course they get warmer temperatures, increased convection, and more rainfall over that part of the world. So a lot of that is pretty well known. But the impacts on our rainfall are summarised in these two graphs. And again, El Nino to the right. And this is simply based on historical observations. They've looked at well over 100 years of data, and they've looked at a number of La Ninas over that 100-year period, and they've constructed a diagram which shows you where the chances of getting above average rainfall are. And so green, light blue, dark blue indicates during a La Nina event, the chances of getting above average rainfall are enhanced over much of Australia. During El Nino, based on 14 El Nino years over that long time period, they can construct a diagram which shows you the yellow, pink and red where the chances of getting below average rainfall are enhanced. And you can see that in both cases, New South Wales, particularly northern New South Wales and even western New South Wales is affected or is subject to the impacts of these events because of the strong colouring that is in that region. In addition to El Nino, La Nina, I'll only just mention there is another sea surface temperature pattern which affects rainfall mainly during winter and spring. It's called the Indian Ocean Dipole. Similar to the El Nino, La Nina sea surface temperature patterns, when we see contrasting patterns of sea surface temperatures across the Indian Ocean, we can discern an impact on rainfall. And again, the maps there indicate when the Indian Ocean dipole pattern is in one phase, when you get drier than normal conditions, that's the left-hand graph. And in the opposite phase, you get above average conditions in that situation. The impact, there is some impact on Western New South Wales, but again, it's not as strong as El Nino, La Nina, and it's confined to usually late winter and spring, but I won't talk about that anymore, other than to point out what the current situation is. And this is what the current sea surface temperature patterns look like. This was the pattern observed on the 21st of February, and you can see clearly a strong La Nina pattern, whereby the temperatures to the north of Australia are all above average because of the yellow and red colouring, and they contrast with the blues off the coast of Peru, off South America, on the other side of the Pacific Ocean. So it's a classic La Nina situation. And a lot of what we've seen in the weather and the events over recent months is just consistent with what we'd expect from a La Nina pattern like this. The pattern is long-lasting. It doesn't disappear in a hurry. So once you see a pattern developing and becomes established, you can be pretty certain that you can make some sort of prediction, or at least make an educated guess as to what your part of the world might experience in terms of rainfall over the coming months until this pattern dies away. And to give you an idea of how this is used in practice, this was an outlook which was prepared late last year. And in actual, this diagram was based on what the Bureau thought was going to happen for spring and early summer, based on the sea surface temperatures which they observed way back then. And it's a very interesting graphic, because the greens and blues on the diagram indicate where they expected rainfall to be above average, but the Bureau have added extra information based on their knowledge of history during these events. For example, they were making comments about the tropical cyclone season to the north. They were indicating flooding was flash flooding due to storms, riverine flooding due to widespread rain. This is in Queensland. Severe storms, southeast Queensland. Thunderstorms, wet conditions, severe storms down in Victoria. Now, again, this is an outlook. It's not a definite prediction, but it's interesting in that it provided some advance warning of what sort of severe weather events could be in store for us. That's way back in early spring of last year. In fact, this is a document that was sent to Cabinet, I believe, and I've seen it posted up recently. I'm not sure whether the public were aware of this. That's just another interesting sideline, but people have commented how much advance warning there was provided to the authorities by the Bureau that early in the piece. So how good was their outlook? Well, you can see this is from September to February of this year. This is the spring, summer period. This is what actually happened. All the blue areas show you where all the rain was above average, and very few regions experienced below average rainfall. Western New South Wales experienced above average rainfall. So that outlook has to be described as potentially very useful. What about for the next few months? Well, the latest outlook by the Bureau is represented by this diagram, which shows you where the chance of receiving above median rainfall is above the normal chance. The normal chance is 50%. And if we focus in on Western New South Wales, the chance of receiving above median rainfall over the next few months is indicated by the green or the light green patterning there on the map, which means it's somewhere between 60 to 70%. In other words, a 10% or 20% shift in the probabilities of receiving above average rainfall over the next few months. Given that this was issued on February the 24th, and the fact that there's flooding now in Broken Hill, unfortunately, well, I'm not sure whether it's fortunate or not unfortunate. It's somewhat reassuring to know that these outlooks do provide some form of advanced information. It's unfortunate when the outlooks prove to be not only correct, but they underestimate what's actually happened. So I hope you're all okay there with the reported flooding there in Broken Hill, etc. So just to summarise that part of the talk, rainfall is extremely variable in Australia. Some of this variability is related to variability of ocean temperatures in the Pacific and Indian Oceans, and this allows seasonal rainfall outlooks to be regularly prepared. Now, moving on to the next bit of the talk, how has climate changed? And I've talked about the work of climate scientists trying to detect trends in the data. Well, if we just have a look at temperatures, then this is a well-known graph showing annual global mean temperatures since 1880 right through to 2020. Sorry about that, 2020. So it's a long-term record of global annual average temperatures. And the interesting thing is that you can see that there is a definite rising trend in temperatures, especially after 1950 or thereabouts. And this data is based on all the thermometer readings that people have been gathering over the past 100-odd years. They've all been collected, analysed, adjusted, corrected thermometer readings over land and over the oceans from ships. A hell of a lot of work goes into preparing a time series like that, and that's as best as we can establish is the true record of global annual average temperatures. Now, the fact that the warming's taken place has been disputed by some people, but it's fairly unequivocal because, as the Intergovernmental Panel on Climate Change states, scientific evidence for warming of the climate system is unequivocal. So there's very little doubt amongst the scientists. And even if there is any doubt that the globe is warming, you only have to look at what's happening in the environment and look at the impacts. And you can look at a whole variety of indices which have reflected warming, including, for example, the fact that glaciers around the world are all retreating. The majority of glaciers are thinning and retreating. The amount of snow cover is decreasing. Sea levels are rising. In particular, the sea ice, which surrounds Antarctica and the North Pole, has been decreasing remarkably over the past couple of decades. And right at the moment, the sea ice around Antarctica is at historic lows. So it's just another index that backs up the temperature record. You can see the impacts fairly clearly. Over Australia, we can also calculate the annual average temperature over Australia and plot it as a time series. We have quite a good temperature series of, a large amount of thermometer readings that have been made very carefully over the past 100-odd years. And the Bureau has been able to assemble those and work out what the annual average temperature was over the whole continent and provided this time series. And it looks similar to the global annual average time series I've just showed you. It's got you can just see an upward trend since about 1950, but you'll also see that there are large ups and downs in the time series. And that simply reflects the fact that Australia is very strongly affected by ENSO events, and ENSO events affect annual average temperatures. 2019 was the warmest year on record. That's the red bar on the chart, which is the tallest one at the right there. But other years which would have been La Nina years are either below average, or in recent decades they end up being just neutral. So we've got a warming trend, and whereas you'd expect La Nina years to be colder than average, what La Nina years do now is only provide you with a long-term average temperature, while the El Nino years are just bumping up the hottest years as we move forward in time. If you want to look at where the temperature trends are located, then you can calculate over a time period, in this case 50 years, 1970 to 2020. The Bureau have worked out where the trends in temperature, what the trends are at each location, and plotted them on a map of Australia. You can see here it's almost entirely covered by pink and red. The pinks and reds indicate warming just about everywhere over the past 50 years. There's only one small place in the Northern Territory where it's remained somewhat flat. There's a little blue patch in the Northern Territory, and that hasn't warmed as much as elsewhere, mainly because it's been getting wetter up there. I'll touch on that next. But the general pattern there is for warming, somewhat greater inland and less so around the coastal regions. I talked about trends in temperature. Now I'll show you the trends in rainfall for Australia. Again, 1970 to 2020. The Bureau's calculated the trends in the rainfall for all the locations and plotted them on a graph on the map of Australia. The greens indicate where rainfall over time has increased, and the yellows and browns where it has decreased. Now, you'll see on the left, I've reproduced the Wilcannia annual rainfall time series for the 1970 to 2020. And if you eyeball it, which is always a good thing to do when you look at a time series, is to cast your eye over it and say, is it going up or is it going down? Well, if my impression looking at that, eyeballing it, is, it may be going down a little bit, but I wouldn't want to be too definite about it. And in fact, according to the Bureau's map, Wilcannia falls within the light brown zone, where the long-term trend is somewhat negative. But as I've said earlier, if you were to plot 2021 there, the trend might effectively just disappear, because 2021 I would expect to be above average. And I'm unsure whether this trend that's been there for the last 50 years is what we say, is it robust or is it statistically significant? There's a hint that it might be that the downturn trend is there, but I'd still like to wait and see a little bit before I was too definite. Where the trends are really definite, and there's no doubt that that's a significant trend, is up in the north and west of the continent. All that region which is green has been shown to be highly unusual. That's a strong signal there, statistically significant. And the other region which is also very significant, but which is not apparent on this map, is Western Australia, which has experienced declines in rainfall, which are particularly unusual in a historical context. So there are hints of trends, and the question is now, well, let's summarise what we know about New South Wales in terms of temperature and rainfall. it's already experienced the impacts of climate change. All of New South Wales has warmed since 1910 in particular. Inland areas have experienced relatively more warming than coastal areas. Annual average rainfall over New South Wales since 1900 shows large decadal variations, but no long-term trend. And that statement reflects my somewhat reluctance to say that there's a definite long-term trend over New South Wales. But the number of days with dangerous weather conditions for bushfires has increased across the region. What caused these changes? That's the next question. And it's a vital question, because people, if you've listened to the news recently and listened to people talk about the floods and linking extreme events such as flooding to climate change, the question is a difficult one to answer, but there is mounting evidence that these extreme events can be associated with the observed warming that we've seen, and the observed warming in turn is linked to increases in greenhouse gases. But in general, what scientists do in trying to attribute observed changes in the climate, such as trends in temperatures or rainfall, is they resort to climate models. And this is meant to indicate that they are complex. I shouldn't really put a slide like that up for a public presentation. It's got too much detail in it, but it's merely meant to give you an inkling of the complexities of climate models, which are just like the weather forecast models, which are used to produce the weather forecast you see on the news each evening, which show you what the pressure patterns are doing, what rainfall will be like tomorrow and the next few days, and what temperatures will be doing, and so on. They're essentially the same models, except they are run not for just a few days, but they're run for decades and even centuries with various inputs to see what how the statistics change as a function of the inputs. And the complexity, the fact that they're complex is because they have to include all the elements of the system: the sun, the atmosphere, the oceans, the land surface, and a whole host of processes. And one of the inputs that we use to drive these climate models is the amount of carbon dioxide in the atmosphere, because the amount of carbon dioxide in the atmosphere has a big effect on the radiation, or the long wave radiation, which reaches the surface, and in turn the temperatures at the surface. And in this case, when we look back in the past, trying to explain observed trends, we can prescribe the known variations in carbon dioxide over the past 100 years or so. Here we've got a plot of what the CO2 concentration has done since between 1960 and 2020, as measured at the mountain observatory Mauna Loa in Hawaii, which is the gold standard for CO2 measurements. And you can see that just in that period, 1960 to 2020, the concentration has gone from about 300 to over 400. In other words, it's increased by over a third in just 60 years. And if we compare that increase, we have a look at how that compares in a historical context. The red arrow shows you where the concentration is at the moment, up around 400 parts per million. That's the right-hand side of this graphic. And if you go back in time, the concentrations that people have worked out based on ice cores going back 20,000, 40,000, 60 and 800,000 years before present, they can measure what carbon dioxide was doing back in the past. And nowhere in the past is there any evidence that CO2 levels are as high as they are today. So that is some cause for concern. And so in trying to attribute observed climate changes to changes in the inputs, I'll try and explain this graph. It's the result of two sets of experiments with climate models, and it's looking at global average temperatures as observed and shown by the black curve, going from 0 in 1850, the observations show going up and down, and up to over +1 degrees by 2020. And the two sets of experiments with the climate models are indicated by the green and the pale brown colouring. And to cut a long story short, if you drive these climate models with the only things changing in them are things like variations in the sun or changes in the atmosphere due to volcanic eruptions based on observation over the past 100 years, the temperature goes up and down and follows the observations till about 1950. Then after that, the observations depart rapidly from the model results. They go up, whereas the models just trundle along doing what they do, what they've done normally, showing ups and downs. They cannot explain the recent observed warming using just the solar and volcanic forcings. But if you then throw in the variations in observed carbon dioxide into the mix and run the models over that same period, again, there's not much difference between the two sets of experiments until about 1950, when the effects of the increased carbon dioxide concentrations are revealed as an increase in the simulated temperatures, which match the observations pretty well. So the take-home message here is that as far as the climate scientists can tell, there are no other drivers of the climate that can explain the observed warming other than the increasing in the carbon dioxide concentrations. And that's why we call that an attribution study, or that provides the basis for stating that we can see the effect of, we can relate observed climate change to increases in carbon dioxide. Now that's well and good for explaining the past, because we know what all the drivers are, and we can say, yeah, that's fine. What about the future? What can we say going ahead? Again, they use the models, and they run the models as I've just shown you from the past, 1850 right up to 2020. But then they keep running them forward. They don't just turn them off. They let the models run forward in time. And what they do then is they keep prescribing changes in greenhouse gas concentrations going into the future, but they have to guess what the greenhouse gas concentrations will be like. And a lot of work goes into trying to estimate what those concentrations will be, depending on what humans do with respect to burning fossil fuels, or attempting to get to zero net emissions, for example, by 2050 or earlier, or possibly failing to have any effect on greenhouse gas concentrations. So there are various scenarios that they investigate, because we don't know exactly what will happen. And you might hear reference to this in your reading, or if you're listening to discussions about climate change projections, greenhouse gas concentration scenarios. And these scenarios are given various acronyms: SSP 119, RCP 2.6, RCP 8.5, for example. And they all represent different concentration, different pathways going forward. Some are unchecked and worst case scenarios. Some are very optimistic scenarios whereby we assume humans can cut back on their emissions and slow down the increase in greenhouse gas concentrations. And as I say, the models are run forward in time. And in this graph of global average temperatures, you can see the results. First of all, we have the results from 1950 to, in this case, up to 2015, showing you the observations or the model results up to the present. And then the trajectories going forward right through to 2100, the different trajectories for the temperatures correspond to those different emission scenarios. And the most optimistic one on this graphic is SSP 1.1.9, assumes, I don't have the exact details, it assumes drastic cuts to greenhouse gas emissions in the near future. The one at the top, where the temperatures keep rising and rising and rising up to almost 5 degrees, is the worst case scenario, where effectively nothing happens in terms of checking greenhouse gas emissions. In all cases, the temperature, it will be warmer at the end of the century than it is now. It's almost impossible to start cooling. We can't do it. We can't remove greenhouse gas concentrations quick enough to having effect on the heating that's already built into the system. But governments around the world they've decided that they would like to keep the final temperature rise to less than 2 degrees, which means committing to the emission scenarios, those two lower emission scenarios where the temperatures, even though they keep rising, at some point they steady and they start to maybe decrease slightly towards the end, but are still warmer than the present day. And you'll have heard about the COP agreements among governments recently to aim for zero net emissions by 2050 as a way of trying to maintain the trajectory to less than 2 degrees. Above 2 degrees, governments have decided the impacts it's too expensive. Things are, we can cope and adapt to 2 degrees or less, but anything more is probably it's becoming too serious. The patterns of increased warming at 1.5 degrees is indicated by the map on the left. If it got to 2 degrees, then it's the map in the middle. If it got to 4 degrees, you're dealing with the map on the right, and you could see, I think that the greatest warming occurs in the polar regions. That's where all the ice and snow begins to melt. And over the middle of most of the continents, it's warming most over the continents, and it's slower to warm over the oceans. What about rainfall? Well, at 1.5 degrees warming, the pattern of rainfall change is on the left. And again, for 2 degrees, the pattern is in the middle. And the yellow means, and browns are decreases. And again, the light greens and darker greens are increases. Or at 4 degrees, you start to see rather large changes in rainfall. And you see patterns of increases over some continents, particularly over the Pacific Ocean and over the polar regions. But you can also see patterns of drying over some of the oceans, and particularly off southwest Australia. In addition to projected changes in just the total amount of rainfall, there's also the possibility that the intensity of the rain when it falls will become greater. And there's some simple physics behind this projection of this observation. That is, as you warm the atmosphere, it holds more moisture. It's capable of holding a lot more moisture than normally. And when it comes time to rain, it dumps more rainfall than it would normally. And the estimates based on the climate science for a 4-degree warming is that the intensity of rainfall could be of the order of 30% more greater than what we normally expect. If we kept it down to 1 degree, 1.5 or 2 degrees warming, we're dealing with increases of maybe 10, maybe 14% max, which may be bearable, but 4 degrees represents a 30% increase. And what would that look like for a place in Western New South Wales, you might ask? Well, here I've attempted to indicate what that means by looking at a time series of daily rainfall now for White Cliffs Post Office. And all the blue bars on this chart correspond to daily rainfall measured over a 6-year period, or just over 6 years, 1996 to 2012. There's nothing special about this period. It just samples the types of intense rainfall events that occur in Western New South Wales. And there are 3 big events in that approximate 6-year interval where the rainfall intensity, the daily rainfall exceeded 60 millimetres. And of course, there were quite a few rainfall events which fall between, for example, 40 and 60 millimetres, but they're the 3 biggest ones in that 6-year period. And the little red bars on top of the blue bars indicate a 30% increase, which potentially could happen in a 4-degree warmer world. Now, the question here, and there's no answer to that, is that a serious, would that cause serious impacts for the people of Western New South Wales if the daily rainfall was, for example, the highest amount then was 90 millimetres at some point in 2011? Do the roads and systems cope with those intense events? Could they cope with one of maybe 120 millimetres, or are the systems capable of dealing with these intense rainfall events, say they occur, the ones that occur now occur, say 3 times in 6 years. Once every 2 years, you'll get a large, intense rainfall event. If you add 30% to all of the bars on this chart, that could double. Would that be a problem? I haven't got the answer, but I'm just pointing out that could be a consequence of climate change. Even if, for example, the annual rainfall doesn't change in the future, this could be something else that could change. You're getting more intense rainfall. So we can move on to like a summary of what is expected for New South Wales and Western New South Wales. For example, under a high emission scenario, the climate of Sydney is projected to be more like the current climate of Grafton. That of Broken Hill Bay may be more like the current climate of White Cliffs. So that's in terms of changes, mainly in terms of changes in temperatures. There will be longer fire seasons, higher sea levels, so that won't be an impact for you guys. Summer rainfall, now we haven't dealt with the seasonal changes, only the annual ones, but summer rainfall is expected to increase over most regions. Winter rainfall is expected to decrease in many regions. Extreme rain events are projected to become more intense, and there's an increase in snow melt along with a decline in rainfall. And that's the general summary for New South Wales, but it's possible to look up detailed specific information for your region by looking at the various sites available and provided by the government and put together by the Bureau and CSIRO, etc. And remember that graphic I showed at the start? Well, here it is again, which is a summary of projected changes for Western New South Wales. So you can see here the four major towns: Broken Hill, Wentworth, Cobar, Burke. Increase in temperature, increase in evaporation, increased rain in autumn, decreased rain in spring, decrease in snow, increase in fire risk is what's projected. Specifically, if we highlight Western New South Wales, we can look at things like the number of days above 35 degrees. And this is what projections, what people are suggesting might occur at 2060 to 2079. That is an increase in number of days above 35 degrees. It's colour. There's a map here of colours. I've just indicated plus 10 days here, plus 20 days there as you head further north. We can look at there's a slight variation in the predicted change in annual rainfall. Well, here they're suggesting a slight increase, maybe plus 5% in the southern half of the region, possibly plus 10% in the northern half. And this would be based on the fact they think summer rainfall would be increasing. This is a map includes all of New South Wales, and just as a side observation, you can see here that already this year marks the wettest start to a year on record for Sydney, with 872 millimetres. The previous record was 816 millimetres. So even though this is a projection for 2060, we have to acknowledge that that's not too far away, and we're starting to see, at least for Sydney, a record that's just been broken, which is consistent with these projections, which is just another straw in the wind about what might be happening in the future. Fire danger days. This is an impact of increasing temperatures. The increase for Western New South Wales, probably an increase by 2060, 3 high fire danger days in a year at 2060 onwards. High fire danger days is based on an index which takes into account temperature and various other factors. So it's another 5 fire danger days. And so I'm getting close to the end of the talk now. There are impacts elsewhere of warming, particularly, as I mentioned, if warming exceeds 1.5 degrees, the coral reefs are at great risk. And not only the coral reefs, but snow depths are at risk, with an impact, probably impacts on winter tourism, given that there will be increased temperatures and fewer cold days. So to summarise, the impacts of projected climate change are serious in that some systems may go beyond their ability to cope if global warming continues unchecked. And there are two responses to projected global warming. It's important to both to try and mitigate them by, as I say, aiming for the world as a whole, aiming for reduced greenhouse gas emissions and adapting to the warming that will take place, given that as I've already indicated, some of the warming is already built in. We can't escape it. All we can do is limit it. With regard to changes taking place around the world, then this is just the latest news coming out from California that remember, we're in a La Nina situation. So this side of the world, we're getting wetter. That the other side of the world, the other side of the Pacific is getting, experiences dry conditions. But California is suffering two things now. The start of this year has been the driest in California's history. With severe drought now in a third year, the state faces depleted reservoirs, a meagre snowpack in the Sierra Nevada, and a worsening water shortage on the Colorado River. And the last slide I'd like to point out to you is this recent report that has just been put out by the IPCC. And one of the important messages from this report is that they stress that the time left to mitigate the changes that are coming, we're running out of time. The window, the opportunity to not to mitigate, to adapt to changes is running out. So mitigation is important. There's no dodging the requirement to mitigate, but time is moving on, and the window for adaptation is narrowing. So discussions around impacts and what to do about them are therefore important. And on that note, I'll finish up, and thank you to my audience for listening.